My name is Mitch Beaumont. I'm a solutions architect and I work for Amazon Web Services in Sydney, Australia. And I'm joined today by Kelvin Zhu, who's a productivity team lead developer from Okta. Let's get started. I love this quote. It's by a guy called Mario Andretti. Does anyone know who Mario Andretti is? Hands up if you do. Excellent, great. So if you don't know, he's a very successful American race car driver. And the quote, I love the quote. It implies that you can't always be in control when you're going fast enough. So if you're not going fast enough, then if you and your team aren't going fast enough, you can often run into issues. What happened to Mario, unfortunately, he lost control of his car. He was going extremely fast one day, accelerated, and his speed outweighed his control. And unfortunately, off the back of that, he smashed into a wall. Now, Mario was fine, no major issues, damaged a few toes, but it kind of resonated with me, this quote, because I think a lot of people decide to use containers because of the speed benefits that come along with containers. So the acceleration and agility that come along in terms of packaging, building, and deploying our software. But just because we have these new superpowers and we can package and build and deploy our software a lot more quickly now, doesn't necessarily mean we need to overlook the security and the controls that we should be thinking about when we're deploying our software. So over the next 30 minutes or so, I'm going to talk you through what I think are some of the really important aspects of container security. Then I'm going to hand over to Kelvin, who's going to talk to you about how Okta have implemented some of these controls across his deployment pipeline for some of their solutions and software. Now, just as a bit of a disclaimer, this is by no means an extensive list. The things that I've listed out here should form part of a multi-layered strategy or an approach for securing any type of container-related infrastructure that you might be managing. And for that matter, any type of application infrastructure that you might be managing as well. So I'm going to talk about kernel security and host security first and foremost. This is where we're running our containers. Then I'm going to zero in on denial of service, and in the context of containers, that's typically relating to resource availability. And we're going to talk about container breakouts, what that means for a container, and what we can do to mitigate the damage that can potentially be caused by that. Then I'm going to look at container images themselves. What can we do with those container images to make sure that we have the right software in them, we don't have vulnerabilities in them that can be compromised. Then we're going to talk about credentials and secrets management, which is a much bigger problem when we start to think about containers, because we typically run a lot more containers than we have done with virtual machines. And then we're going to take a quick look at runtime security. What happens when we run these containers at scale in the environment, in production? How do we make sure that those containers continually have the latest vulnerability patches and security patches applied to them? So without any further ado, I'm going to take you on this journey now. We're going to start by talking about kernel and host security. Lay the land a little bit. Let's start by just setting the scene. There's obviously some very different fundamental security differences between virtual machines and containers. As you can see on the left-hand side there, we've got a bunch of virtual machines running on a hypervisor. The applications within those virtual machines are isolated from one another at the kernel level. Each guest operating system has its own kernel. On the other side then, we've got the container instances themselves, or we've got a container running on a shared kernel. So that's the isolation that's used to wrap around a container is used through implemented using Linux namespaces, and there's a range of Linux namespaces that are used to specifically isolate the processes and capabilities of those applications. We need to think about the security of those containers slightly differently, because the implementation of that isolation is a little bit different to what we were used to when we think about virtual machines. Those containers share a single kernel. They also access a set of common shared files, sockets, memory areas, and devices on their host operating systems as well. So as I said, the posture is slightly different to that of a virtual machine, and with that we need to think about how we handle security slightly differently. When we think about running containers on AWS, we typically run them on top of EC2 instances, and those EC2 instances are created from Amazon machine images, or armies as we tend to call them. So let's have a look at what we can do when we're building these armies to make sure that they are nice and secure and we don't run the risk of necessarily getting compromised. We look at, initially we take a base optimized image from the public repository or the public catalog. In this instance, I've decided to take the ECS optimized army. That optimized army has a number of tweaks and standard pieces of software that we embed in there for our customers to use. Next, we take that and we build a foundational AMI or army. That foundational army includes very specific, domain-specific, in fact, configurations that we may desire within our environment. That can be specific security controls, can be provisioners, can be log management tools, and other config-related items as well. Then finally, we create our final full stack army, and that includes all of the rest of the dependencies that we need to have our army operational and running to be able to execute and host our containers themselves. It's really important that we build our armies this way rather than relying solely on the base public images that are available in the catalog, because as many of you probably know, Amazon from time to time deregisters or depreciates some of those armies, and if we don't do that, that can potentially lead to an availability issue in terms of those armies in the future. Another really important part of this process is that the steps that we go through to configure those armies, it's important that we codify those or codify those, depending on where you're coming from. And what I mean by that is that the steps that we go through, the configuration changes that we implement, the security best practices, we capture them in code and we store them in a central location. And the reason we capture them in code is so that we can replay those in an automated way, so we can continually rebuild new versions of our armies as updated versions of those armies get released by AWS. Once we have that codified version of our configuration, we're able to pass that into a deployment pipeline, and we can use that then to continually publish or create armies for us to use on an ongoing basis. It's extremely important, as I said, given the shared nature of much of the operating system for our containers, that we have an automated way of building these armies so that we can provision and publish and update our fleet of instances on a fairly regular basis. So here you can see I've got my DevOps persona. He's pushing his configuration into a code repository. That's then triggering a pipeline job. The pipeline job then is dipping into our public repository and it's pulling out a base image. So let's say it's the ECS optimized image in this instance. It's pulling out that base image. It's then layering down the specific configuration items that we have in our codified configuration document. The output of that is then a domain specific or a customer army, which we then inject back into the pipeline, and then that can be passed on to the next step in the process, which in this case is CloudFormation, but that could be any other process. It might be that we're using Terraform or any other tool to orchestrate the deployment and the provisioning of new instances with this new army. Sorry if everyone got that. So let's talk about denial of service now. What's denial of service in the context of a container? Well, as I said, the containers share lots of resources. Specifically, we think about things like CPU and memory. There are other resources as well that get shared, so things like user IDs get shared within the containers on the instances themselves. What is container breakout? Well, a container breakout occurs, sorry, my apologies, jumped a bit too far there. What happens then, what is a denial of service? A denial of service occurs when one of those containers decides that it wants to consume more resources than it should be consuming. So in the example, I've got here two containers. I've got a cats container and a dogs container. My cats container decides that it wants to consume all of the memory that sits on that EC2 instance. What eventually happens is we push out that dogs container, which means the dogs container can no longer service requests, and we end up with a denial of service. What can we do to mitigate and limit the impact or the probability of a denial of service attack happening in this type of scenario? Well, first and foremost, it's really important that we understand the resource requirements of our application. Because using tools like ECS, we can declare and define upfront the resource requirements for our containers, and we can make sure that our containers only have access to those specific resources. In the event that they try and take more than they've been allocated, we can actually invoke a termination of that particular container, which saves us a whole world of pain in the future. But it's also not just memory and CPU. Those are the main ones that we typically look at. Memory probably being one of the most important ones, but because applications have a tendency to steal lots of memory. But also we've got things like user IDs that exist there as well. So it's worth understanding what resources we can reserve and limit. Next point is to monitor always. So make sure that we're monitoring the usage of these resources continually so that we understand the patterns. What is the expected behavior of the container application? And when we start to see anomalies across that, we're able to take action and remediate. Great tools are out there by some of our partners, including people like Datadog, that give you very granular visibility into the type of resources that are being consumed and are able to give you notification and advise you when things are looking a bit erroneous. And leveraging auto-scaling I've put there as well. This is a nice capability of ECS. Obviously, ECS is very integrated with AWS. So to combat these resource constraints that may occur because of a rogue container, we're able to scale our fleet of EC2 instances under the covers, which means we've got additional capacity available to soak up that load. But we can also scale the containers themselves. Right, container breakouts, which is where I got to earlier on. My apologies for that. What is a container breakout in the context of container security? Well, a container breakout occurs when a process or application is elevating privileges and able to break outside of the container construct or the isolated environment that's there for it. So what I mean by that is My apologies, yeah. Sorry. Not all processes get namespaced within the container. Specifically, user IDs don't get namespaced by default, which means that those processes that run under certain privileged user IDs can potentially break out of those containers and compromise the underlying operating system. What's the best way to tackle that type of problem? Well, first and foremost, I would strongly recommend that we don't run any processes within our containers as elevated users. Most of you that have configured Docker files before will notice there's an argument that we can typically set in there that is the user. It's often overlooked and it's often left to the default, which is to run as the root user. Changing that helps a lot and mitigates the likelihood of an elevated privilege, a privilege escalation. What else can we do to combat that? Well, segmentation is a good approach. What I mean segmentation is by taking those containers that perhaps are slightly more critical or sensitive or have a slightly higher risk profile and separating them from one another to make sure that in the event that a container breakout does occur, other workloads are not impacted by it. The segmentation process or criteria may be, as I said, the risk profile, the level of exposure, the sensitivity of the data that's going to be traversing through that particular container. How can we go about doing that? How can we make sure that containers that are of a specific sensitivity or classification operate on distinct container instances within the environment? ECS has a really nice solution to this problem. I'm sure other container orchestrators do as well. But in the example you've got here, what we've got is we're placing an attribute or a custom attribute on one of the container instances that we're running. That custom attribute is basically saying this container instance has a card data environment and it has a value of true. Then, when we create our task definition and we deploy our task, the schedulers will observe and honor that attribute that we've set on the task there, and it will only place the tasks of this particular task type onto the instances that have that CDE value equals true. That way we're able to segregate all of our containers from one another. So as you can see now, what we've got is we've got two distinct sets of container instances. We've got a CDE set of container instances that have been separated, and then we've got the non-CDE set of container instances there. So our dogs and our cats are running separately from one another. Typical Docker networking by default allows what we call inter-container communication. What that means is even though we've isolated our containers now by risk or exposure profile, those two containers, the cat's containers here and the dog's containers on the other side, can still potentially talk to one another if certain steps aren't taken to mitigate that. One of the things that we can do is we can change the Docker configuration to inter-container communication equals false, and that will essentially stop those containers talking to one another through the Docker bridge to which most containers get connected through a default mode of networking. But with the introduction of some additional capabilities in the ECS space recently, there's a few more things that we can do to potentially combat that now and keep things nicely packaged up and isolated away from one another. One of the capabilities that we announced recently is something called Task ENI, or Task Networking. Task ENI, or Task Networking, is a capability by which we're able to associate an ENI, or an Elastic Network Interface, with a specific task within an ECS cluster. What that means is, traditionally, all containers on a given ECS instance would communicate via the Docker O bridge, which is a network that gets created on all Docker hosts. They would then communicate through that Docker O bridge out via the primary ETH0 interface, which is on each of the container instances. That can be very difficult to stomach if you're doing network analysis and you're trying to diagnose capture traffic that's coming out, because everything appears to be coming from the same location. It also means that, unfortunately, because we only have a single Ethernet interface attached to the container instance, we're only really able to apply a single security group to that set of containers. They all have to have the same security group rules applied to them. So with the introduction of task networking, now that we can assign an ENI to a specific task, we can go a little bit more granular in terms of the isolation between those containers and the egress and ingress of the traffic between them. So this is the typical approach. This is how it worked before. The Docker O bridge is there. We've got this global namespace. We've got the ETH0, as you can see, and we've got the route table within there. With task networking, the way it works is when we spin up a new container, assuming that the task definition includes the networking mode of AWS VPC, what will happen is under the covers, ECS will provision us a new Elastic Network Interface. So here you can see that we've created ETH1. The next step in that process is for the ECS agent, which is a container that runs on top of the, inside of this global namespace here. That will invoke a series of plugins which have been written to the CNI, or Container Network Interface standard. Those series of plugins will take that new ENI, that ETH1 ENI, and move it into the new networking namespace that's been constructed for the container that we've just started. Now the container that we've just started in this network namespace, all traffic that's egress or ingress will traverse that ETH1. Because it's an ENI, it means we can now attach, as I said, a security group to that. But it also means that we can do a little bit more. So if we're trying to use network diagnostic tools and troubleshooting tools, and even network analysis tools, we can be a lot more specific and targeted when we're doing our investigations, which is a really powerful tool capability. What other things can we do to limit the damage that can potentially be caused by a container breakout incident? Well, we've got things like capabilities, Linux capabilities, and these are kernel-level system calls that we can restrict on a container-by-container basis. Here you can see we've got an example. We've got a cats and a dogs container. Up until very recently, it was very difficult to write these capabilities out using task definitions. Now we've introduced that capability into ECS, so we can use those capabilities to block those privilege levels calls out to the underlying kernel. As you can see, we've disabled the chown capability for the dogs container, and the netbind service capability there has been enabled for the cats container. Adding those capabilities and dropping those capabilities is fairly easily done. That's how you would typically do it using the docker run command. And then underneath that there, you can see an example of the JSON that we would use within a task definition to achieve the same thing. Image security. All of our containers are made from images. That's basically the price of admission when it comes to using containers. The question I'd probably ask everyone here is, does everyone know what's inside of their containers? I'm assuming most people pull their containers from public repositories. Hopefully a lot of you use private repositories as well. But do you really know what's inside of all your containers? And generally speaking, unless you've built those containers from scratch, literally scratch, you probably don't know what's inside of those containers. And if you do, that's great, but do you maintain what's inside of those containers? There's lots of things going on there. There's lots of software that's continually added to those containers over the life cycle of those containers. And many of those pieces of software potentially could develop vulnerabilities that need to be patched and addressed. Another problem that can occur within our images is privileged binaries that exist within there. So here we've got some binaries from a typical image. These are binaries that are set with the set UID flag. This means that they essentially execute as the owner of those binaries, which typically is root. So if you were to execute any of these commands within a container, they would be executing as root. And obviously, once you can execute as root, there's a whole lot more you can do. How can we address that problem? Well, first and foremost, we can go through our images and we can make sure that either A, we don't have some of these privileged executables or binaries within our images, or we can go through a process called defanging, which is to go through and actually remove this set UID ID flag from many of these binaries. Be interesting to see when you go back, perhaps check some of your images, see what's in there, and have a guess whether or not your applications rely on these things. I'm sure many of you would find that probably not so much. Here's an example of an image history I pulled recently. I was just looking at a HTTP image, just to give you an example of the types of layers that go into a single image. There's lots of activity there, and much of the activity there wasn't actually driven by you as the consumer and user of that image. Every single piece of software or change that's been injected in there needs to be factored in when you're thinking about security of these images. What are some of the best practices then when we're creating images? How do we create secure images? What should we be doing? Well, we should be thinking about using signed container images, making sure that we're pulling container images from trusted sources, making sure that the images we are pulling are images that we expect to be pulling from trusted owners. Other things that we can do is set file systems to read-only. This means that those containers themselves won't be modified and potentially stops any bad actors from getting there and making changes which could be used to compromise the container. As I've already talked about, we can remove set UID and set GID binaries from the images themselves, or go through that process of defanging, which is to remove that flag from those binaries. I already talked about not running your containers as root. So making sure that when you're defining your Docker files, you include that user argument in there and specifying a specific user that is non-root. And then finally, I've put there, consider running static binaries. If you've got a static binary, there's no other dependencies that you need to worry about. Everything's packaged within that binary itself. The only downside or drawback of that is that it can be a bit difficult to try and troubleshoot and diagnose and debug these containers if you've just got static binaries in there. General image security tips and best practices. Make sure we're using trusted images. Make sure we're pulling these from trusted locations. Private repositories, ideal, would be great. Make sure we're using minimal base operating system images. And that doesn't just necessarily relate to the containers themselves, but also the host operating systems. Make sure we're using things like Alpine. If we can build an image from scratch, even better. Scratch again, quite literally scratch. And image signing as well, to make sure that the images that we're pulling down are those images that we should be pulling down. They haven't been tampered with, they haven't been manipulated beyond what we expect them to be. And then look at using some container vulnerability scanning tools. There's lots of them out there. We've got lots of great partners that integrate with ECS and ECR. I've listed a few there, so Twistlock, Neuvector, Aquasec, you name it. And all of those tools are really good tools at helping you scan continually the containers that you store within your, the images that you store within your registries, and notifying you if there are known vulnerabilities and helping you take actions to remediate that. Here's a typical kind of workflow that we might incorporate when we're building these images, that we might build with our DevSec and Ops engineers. So our developers and our security engineers have a vested interest in what we're deploying and what we're writing. So here we've got a Docker file, we've got a task definition. We're feeding that into our code repository over here. Our engineers are obviously contributing also, our operations guys. We're then building a Docker image based off of that. We're performing some checks before we build that Docker image though, so we're making sure, we're doing a lint here of a Docker file, and we're making sure that within that Docker file itself, there's nothing in there that we consider to be bad practice. So here you can see we're looking for making sure that the user instruction is there. If the user instruction isn't there, this build process is going to fail. Also making sure that we don't have SSH installed as part of the process. Again, this will help us fail that build and stop the image getting pushed out into production. At the same time, we can run vulnerability scans against the image. Using some of the tools that I already mentioned there. And finally, once we've been through those checks and we realize that our image is in a good state, we can then push it into an image repository for future consumption. Secrets. What are secrets? Well, these are the things that we need to push into our environment. I already mentioned earlier on that this becomes a much larger problem when we think about containers, because there are a lot more containers than there are virtual machines. It was a best practice some time back to put your secrets into your containers and your applications using environment variables. For those of you that ever tried to do that and have ever run a Docker inspect, it's fairly easy to extract that information from a container if it's not encrypted. So generally speaking, we don't recommend putting them in environment variables if it's extremely sensitive information, like passwords and usernames. There's a couple of examples there of why it can be easily extracted. We can take them from ECS API calls, Docker inspect, and link containers, not so much anymore, but that has been an issue in the past. So what can we do as opposed to putting them into environment variables within our application containers themselves? Well, we can store them in other places. We can store them in S3 buckets. We can store them in things like Systems Manager Parameter Store, and I'll talk a bit more about that in a moment. But one of the things that's really empowered us to do this in an effective way recently is the use of IAM roles for tasks. So every task that we now create, we can associate a set of IAM privileges with that task, which limit and control what resources those tasks can create, can access. The role itself is similar to most IAM roles. The policy structure is no different, but instead of assigning it to an EC2 instance, we assign it to a task. Here's an example, IAM roles for EC2. So you can see at the top there what I've got is an IAM role associated with the EC2 instance at the top level. What that means, unfortunately, is that both of the containers that are running within the environment there inherit those same privileges as the container instance itself, which means that we've got a CATS container here that has some undesired privileges and permissions. He's accessing the dogs bucket, and if the dogs bucket contains sensitive secrets that he shouldn't be accessing, we've got a problem there. So with the introduction of container level or task level roles, what we've got now is we've got a very specific subset of permissions that only allow the CATS container to access the CATS bucket and the dogs container to access the dogs bucket. As I mentioned, and my apologies, the naming's slightly off because we've just done a naming change this week, but Amazon EC2 Systems Manager or AWS Systems Manager now, Parameter Store is another approach that we can take for storing those secrets in a central location. So Parameter Store is a fully managed, fully encrypted, highly available secrets management parameter store. Secrets are stored in there. They can be encrypted as secret strings or plain text strings. But the real benefit and the real power of that is it's highly integrated with the IAM, which means that we can restrict access down to the parameters within an environment down to specific tasks. We're using IAM roles for tasks, and Parameter Store, we can restrict down very granularly which parameters those containers can actually access. We can also encrypt using KMS, so we can provide almost a second layer of authentication or validation by granting the container itself access to decrypt those secrets using a very specific KMS key. Here's an example. So we've got a CATS container. You can probably tell I like cats and dogs. We've got a CATS container reaching out to parameter store there. It wants to decrypt the secret, so it's calling on KMS. It's getting the key, it's decrypting the secret, and the secret's then being passed back to the CATS container for use within its runtime. And that was a good segue into runtime. So I already mentioned about the introduction of task networking for ECS. One of the benefits that brings with it, as I briefly mentioned, is that we can now get much better visibility, much more granular visibility into the behavior of the containers that are running on our container instances. Rather than just having to consume all of the information that's coming out of that primary ETH0 interface, we can kind of reason now about what those containers should be doing, the sorts of traffic we would be expecting to see coming out of those containers. So here we've got a CATS container again. He's making a call there over port 22. Now my CATS container is a simple HTTP application. There's no reason why it should be making a call out via port 22, especially not to another container. Because we're using ENIs for each of these containers, what I'm able to do is I'm able to enable something like VPC flow logs, or I can attach another tool and assess that particular interface using a different mechanism. But by looking through the VPC flow logs, I'm able to identify the rejects here and there. I can see that I've got a reject, I've got a connection to port 22 being made, and off the back of that, then I'm able to take some remediation steps or some actions to try and address that particular problem. Now, whether that is go ahead and stop the container, or take some other action, like go and inspect the container to try and find out exactly what's changed on that container, how it's been compromised. There are lots of really great tools out there that can help manage containers at runtime. One of the ones I particularly like is Twistlock. There's a lot of capabilities in there. It does not only image scanning, but it also does vulnerability management at runtime, runtime defense, compliance, native firewalling. It does a lot of intelligence assessment over the applications themselves, so it will model each of the images that you have, and it will indicate when things look erroneous in terms of the application flows between the various containers that are in your infrastructure. So I'd highly recommend, if you're looking for a tool to help you with your runtime container management, take a look at Twistlock. But as I said, there's plenty of other partner solutions out there that can do the job just as well. With that, what I'm going to do now is hand over to Kelvin to talk to you about how Okta has solved many of their problems from a container security perspective.
Is it on? Yep, as mentioned, I work at Okta. I'm a productivity team lead developer. Basically what that means is that I work on the developer tools that all of our developers use in order to get their code in, to master, such as our continuous integration system, and also help out with some of the release tools. And overall, I'll be going over kind of how we utilize containers in our system and how we secure them. Overall, in terms of how I'll go through this, is first I'll go into a little bit of detail about how we use containers in the first place, and then I'll go into the details about how we secure them. So in terms of what security is to us, it's very important to us that we keep our system reliable. In terms of all the different kinds of things that can happen, such as security breaches or improper use of secrets, if any of those kind of things happen, it's very damaging. And also, one very important part of it is it's very, very costly. Basically, if our system goes down, our developers can't use the system. So we want to make sure that that our developers don't have any issues. And likewise, by having a heavy automation inside of our security system, it isn't difficult for us to make sure that we actually have all these security processes in place. So I'll go through some of the examples. In terms of how we actually use containers, I'll go into first a little bit of a high-level overview of kind of how our system works. So a developer, they write their commits, push it into GitHub. What that results in is a push commit notification from GitHub over to our system, which we call Bacon. And in there, the user can see what commits are available to them. And then if they say, hey, I want to run the tests on this system, on this commit, then it results in us sending jobs over to a job queue, which in this case is an SQS queue. And then from there, it goes over to our worker pool, this is where our containers are. They're Docker testing agents. what are these Docker testing agents? They run the jobs, fire off whatever tests they are, do any kind of processing, and then once they're done, they send the results back over to our Bacon web application, where the users can actually go ahead and see, hey, did it was a successful failure or not, and then if they're good with it, then they can merge the results. So this is just what I was just talking about. So digging a little deeper into the containers, basically in terms of the Docker runs, they do various things in them. They might be test runs, they might be builds, but overall in the end, some of those builds actually create artifacts. Now these artifacts could be things like Java jars and PM packages, but they also, some of them are Docker images. All of these go into our repository for artifacts, and then from there we consume them. Some of these actually even go right back into our CI system, the Docker images. They get run as part of our ECS tasks in order to actually be these Docker testing agents. And then others, which are actually web applications, get run on the onto ACS services. In fact, actually, our Bacon web application itself is one of these services that we run. So, yep, again, what I was just talking about. In terms of those two different types, we have different scale that we have to handle for each of those. For instance, for the CI system, it has to scale up to thousands of instances at times because our developers have hundreds of tests that they have to run. And likewise, these containers are also only, they only have to run once, and they generally are done within an hour. But likewise, we also need to scale down the system heavily because like overnight and during the weekends, there's kind of no need to actually run so many containers if the developers aren't actually working. On the other hand, the ECS service side, with the web applications, those ones have to scale up and down according to web traffic. And likewise, these containers are much more longer lived. So now going into the actual security side of things. So in terms of us handling the host side of security, we have kind of three major parts: the AMI, accessibility, and ease of change. So in terms of the AMI, Mitch already talked a bit about them hardening their AMI. But likewise, we also have much of the same issues that we have to deal with in terms of that every single package that's installed is a potential threat. So we also work on creating our own hardening AMI because every single installed package, even if it's unused, like if we use the ECS optimized AMI, even if whatever they have in there, even if it's unused, it might have a vulnerability that we have to patch even though we're not using it. In order to minimize the possibility of that problem, we make sure that we have an AMI with only the minimum necessary to run the application. And in order to make sure that it's security compliant, we also make sure that it complies with all of the Center of Internet Security checklists. Make sure that everything is secure. So what this looks like is we have the Packer build repo, which is essentially just a repository with all the definition of how to build our AMI. And then we have Bacon to process out what are all the things that need to be run in order to actually build this image. And then once somebody says, hey, I have a commit and I want to actually get this turned into an AMI, then they would run off the jobs on Bacon. That results in, on our Docker containers, running the build AMI job. Once that's done building, then we run off some server spec tests on it to make sure that it's functional, that there aren't any issues. If there are any issues, then of course it goes back to the developer and they have to make fixes to it. Then once it's actually done creating the AMI, we then have it run through a couple additional tests to actually make sure that it's compliant. This is where we run off basically the CIS checklist. Once it's done running through those tests, and if everything is okay, that's when we actually run off the additional jobs to actually send it off to all our different AWS accounts. Now, in terms of our CI system, all of it is behind the VPC. So that's one way that we prevent unauthorized access to it, is making sure that everything is behind the VPN. Likewise, we also make sure that we have all of our security groups so that all of our individual EC2 instances that have our AMI running on it aren't able to communicate with each other. We do allow the security groups to actually allow them to connect to some external services if they need it, because our developers sometimes need that kind of access for their jobs. But these instances shouldn't be able to talk to each other because they're running individual self-contained jobs. Likewise, in terms of the SSH keys to actually get onto these instances, we also only give them to a very trusted set of users and make sure that we rotate them regularly to make sure that nothing gets leaked. Now, in terms of making sure that we can change things and patch things very regularly, just in case, like, say, there's a 0-day or something like that, we make sure that it's very easy to create our AMI at all times. Because it's very important for us to make sure that it's very fast also, because if there's a 0-day, we need to make sure that we get it fixed, hopefully within a day, if not less. So, for instance, like this is just a little bit of a snippet of some of the commands that we run using the AWS CLI in order to create an AMI. And so what this looks like is, say that, so basically we have a CloudFormation template, which is, governs basically how we have our EC2 cluster, or ECS cluster, sorry. And it is, that ECS cluster is backed by an auto-scaling group, which brings up more or less EC2 instances as necessary. Now, say that a malicious user comes in and they hack one of our EC2 instances. Now, that instance is hacked, it's actually very easy for us to just plain fix this problem. We just terminate the instance. Because everything is behind an auto-scaling group, once this instance is gone, then our auto-scaling group will just bring a new one right back up. And since we have plenty of other EC2 instances, our users don't really notice any difference in terms of that. Now, in terms of the 0-day, it gets a little bit more complicated, because now all of the EC2 instances are compromised. So in this case, we generate the new AMI using that process that I showed earlier. And we feed it into our CloudFormation template as a new parameter. And in this CloudFormation template, we have a certain update policy, which is an auto-scaling rolling update. And what this allows the system to do is it will just take down a couple instances at a time and then bring up new ones to replace them. This allows us to make sure that we don't actually have downtime in order to replace all of these EC2 instances. So then, once it's done doing its work of getting all of these instances replaced, then we are now back in a good state, and we're not, this 0-day is dealt with. One more thing in terms of all of our hosts and killing them, making sure that we are able to terminate them at any time, is that we also even make it so that we terminate them on a daily basis, actually. We pretty much have a process on them that kills those instances within 24 hours. What this allows us is it makes sure, for one, that nobody goes in and actually makes any kind of manual patch. Instead, we make sure that it's all within our automation, because if there's any manual patch and then we suddenly lose an instance, then that's usually a sign of a problem. Likewise, it makes it very easy for us to have that very quick turnaround. Now, going into some details about container security. Mitch already talked a bit about how credentials should be handled on containers. And as mentioned, having the credentials on S3 and then pulled into the container. So now he mentioned that it's better to have it in memory because it's, though in terms, there's also the option of having it on file, but that's usually not that great because if somebody actually gets access to the container, they can just grab it. In terms of pulling down the creds, though, we do also utilize pulling them down from S3, but there is still a bit of a problem in that since we allow our users to actually run their code on our containers, if they know how our system works, they could just potentially like print out the credentials or something like that. So that's quite a bit of a problem for our system. It's very easy for any of our developers to get the creds if we actually left it at this. So moving on to the next step, what we had to do is that we had to actually, for one, of course, making sure that the developers can't even get the containers in the first place. But likewise, also, we made sure that for access to get those creds off of S3, we hid them behind standard parameterized code that would actually, they could specify, hey, I need this secret, and then this is how I need to use it. But likewise, we only allow them to use those methods to actually access those containers. If they try to do anything in other ways, such as like directly accessing them, then we just plain won't run their script. Likewise, just in case somebody figures out some other way to get around this system, we also make sure that all the logs and output files are sanitized for any of those retrieved secrets. So that also is another way that we prevent any kind of leakage. Now, also in terms of our containers, it's very important, of course, that our developers, they're running all these different kinds of jobs, that they are able to access all the different kinds of services that they might need. Definitely, of course, the credentials that they might need, any kind of databases, maybe some messaging services. There are plenty of different kind of things that they might want to be able to access. And in fact, some of them are even larger than that, such as the ability to create an AMI or something like that. That's also a special permission that they might need. But likewise, we also want to make sure that it's very minimal. Utilizing individual task IAM roles, as Mitch mentioned, is one way to keep that down. But likewise, having a lot of stars is something that plagues a lot of people in terms of their IAM role policies. So in terms of us, how we actually manage to make sure that they are as minimal as possible is we utilize two things that AWS gives us. One is Access Advisor, which gives you kind of an overarching view of like whether or not this role that is running is actually even accessing certain services. Like it might tell you, oh, this role, it's never even accessed SES, even though you've given it that permission. In that case, that's a potential for you to just take out that whole section of that IAM role of access to SES. But likewise, since Access Advisor only gives you information about overall services, it doesn't help you get rid of those stars as much. Instead, for that, we look at CloudTrail logs, because then that actually gives you the individual API calls that IAM role is actually running. And by utilizing that, we can actually see, oh, it's only accessing, say, this bucket in S3 or this topic in SNS or something like that. And then we can trim things down according to that instead of having to do this whole guess and check process. So now going on to image security. Looking back at this from before, basically, as mentioned, we actually generate the artifacts and then we utilize them in our CI system. Now, how we actually do that, though, with the ECS tasks, is that we actually allow running Docker within Docker. So we basically mount Docker from the host onto the container, and this allows us to run Docker and Docker Compose within these containers. So this is used pretty darn heavily by our developers because it allows them to actually test the Docker images the exact same way that they are deployed. They basically can build them in one job, upload them up to our artifact repository, and then they can download them over in another job, run off tests, and make sure that everything is okay. And likewise, in terms of just plain the building of those images, it's also very repeatable because they're running within the same containers every single time. Also, in terms of the creation of our images and usage of them, we also try make sure that they are as minimal as we can. We don't put any of our credentials, our code, or packages on them. Instead, when one of these Docker testing agents comes up, it has to go and get the credentials to be able to get everything else off of S3. So then, once one of these our Docker testing agents gets it off of S3, then it's able to actually go and access GitHub, pull down whatever code it needs to work on, and likewise also pull down whatever artifacts that it might need to actually process whatever its job it needs. Now, how this helps in terms of security is what if a malicious user actually gets one of our images off of our repository? Since they don't actually have the IAM role to access the S3 bucket to get the credentials for everything, then now they basically have a very minimal image that can't really do anything for them. They can't get the code, they can't get the artifacts. So this is one more layer of security on our system. And then in terms of kind of the packages and registries, in terms of our images, likewise, we also make sure that they are built off of an internal base image that is configured to only pull from the internal package repository. These packages that are inside of our internal repository, thus can be actually vetted by our security team and make sure that there aren't any issues, that we don't actually pull down any external dependencies that we aren't sure that we actually want. Likewise, also we make sure that to heavily pin our packages so that we don't, again, pull down something that we weren't expecting. And then likewise, in terms of the repositories that we use Artifactory for storage of our main storage of our images and artifacts. But likewise, ECR actually gives us slightly better performance in terms of pulling down images in order to run, especially for our CI system, because those come up very, very regularly with thousands per day. So we actually make sure that we put any images that we actually need that have already been security approved onto the ECR so that they can be used. So finally, I'll give some key takeaways from what I mentioned. So definitely make sure that you protect from unauthorized access. VPC and security groups are very useful tools for making sure that you limit all the unnecessary network traffic. And IAM roles to make sure that you've locked down all of the access to the creds and services that you need. Make sure that they're as minimal as you can. For problem, making sure that there's a minimal surface area for problems, making sure that you don't install more packages than you need. And likewise, make sure to create very heavy automation. The more automation that you have behind this, the easier it is to actually fix any problems and make any patches, because the security ecosystem is always changing. So that's pretty much it. Thanks. And make sure to complete your evaluations.